Assalamu alaikum everyone, this is Muhammad Amin. I will present a presentation on flow thermodynamics. Flow thermodynamics is a branch of thermodynamics dealing with energy, mass and momentum transfer in system where fluids continuously flow across boundaries. Based on control volumes analysis rather than closed systems, consider how heat, work, enthalpy and kinetic or potential energy interact during flow. In the diagram shown, you may see a representation of control volume with arrows, enters and leaves. These arrows symbolize the fluid moving in and out of the system. This is crucial because each incoming or outgoing stream carries energy with it. The diagram helps emphasize that flow systems must consider both mass transfer and energy transfer happening simultaneously. Flow can behave in two major ways, steady or unsteady. In a steady flow, the conditions at any point in the system do not change over time. In contrast, unsteady or transient flow occurs when system properties keep changing with time. In diagram, the steady flow region is usually illustrated with smooth, constant arrows, while unsteady flow may show changing arrows, thickness, or various properties at different times. This visual representation helps show the difference between stable, predictable operation and rapidly changing conditions. Now let's discuss flow work and enthalpy. We have first flow work. When a fluid enters or leaves a controlled volume, it must be pushed across the boundary. This pushing requires energy called flow work. Flow work per unit mass is given by product of pressure and volume. Flow work represents the mechanical effort needed to maintain fluid motion through the system. Now we have enthalpy of flowing fluid. Enthalpy is the thermodynamic property defined as the sum of internal energy U and the product of pressure and volume, which is called flow work. Internal energy accounts for microscopic energy, molecular or kinetic energy, or potential energy. Now, in the diagram shown, a fluid entering and leaving a control volume with product of pressure and volume work arrows on both sides. This helps visualize how the fluid must be pushed into the device and how enthalpy represents the total useful energy carried by the flowing fluid. The next major concept is the conservation of mass and the steady flow energy equation. Conservation of mass. Mass cannot be created or destroyed. For a steady flow, the mass entering a control volume must equal the mass leaving it. Mass in is equal to mass out. This ensures no accumulation of mass inside the system. Now we have a very important equation. This equation is called steady flow energy equation. This equation is fundamental for determining turbine power output, estimating compressor work requirements, calculating pump energy needs, and analyzing nozzles, diffusers, boilers, and condensers. In the diagram shown, it includes different energy arrows, heat, work, and fluid streams, illustrating how multiple forms of energy enter and leave the system at the same time. This helps the different components of the equation, which is steady flow energy equation. Finally, flow thermodynamics has significant real-world applications, which are steam-powered plants, jet engines and gas turbines, pumps and water distribution, HVAC, chemical processing and refineries, everyday applications. Thank you so much.
Introduction to fluid compressibility. Fluids are classified based on how their density changes with pressure. फ्लूइड्स को हम दो कैटेगरीज में डिवाइड करते हैं, एक कंप्रेसिबल फ्लूइड्स और एक इनकम्प्रेसिबल फ्लूइड्स. कंप्रेसिबल फ्लूइड्स वो होते हैं जिनकी डेंसिटी वेरी करती है विद प्रेशर एंड टेम्परेचर, वाइल इनकम्प्रेसिबल फ्लूइड्स की जो डेंसिटी है वो रिमेन कांस्टेंट रहती है. और इनकी जो डिवीजन है उसकी उनकी इंपॉर्टेंस ये है कि जब भी हम एनर्जी की इक्वेशन अप्लाई करते हैं तो हम ये जहन में रखते हैं कि जो हमारा फ्लूइड है वो वेदर कंप्रेसिबल है या इनकम्प्रेसिबल. अगर कंप्रेसिबल है तो फिर हम एनर्जी की इक्वेशन में इंटरनल एनर्जी का फैक्टर ऐड करते हैं, अगर इनकम्प्रेसिबल है तो फिर हम इंटरनल एनर्जी का फैक्टर ऐड नहीं करते. कंप्रेसिबल फ्लूइड्स के लिए एक टर्म है जिसे हम कंप्रेसिबिलिटी फैक्टर कहते हैं. Compressibility factor tell us how much a real gas deviates from an ideal gas. If the value of Z is equal to 1, then the gas will be ideal gas. If the value is not equal to 1, then the gas will be real. इसके बाद कंप्रेसिबल फ्लूइड्स आते हैं। कंप्रेसिबल फ्लूइड्स को हम इसलिए कंप्रेसिबल कहते हैं क्योंकि उनके जो मॉलिक्यूल्स होते हैं वो एक दूसरे से काफ़ी दूर होते हैं। जब भी हम उन पर प्रेशर अप्लाई करते हैं तो उनकी डेंसिटी काफ़ी इंक्रीज हो जाती है, और जब टेम्परेचर अप्लाई करते हैं तो उनकी डेंसिटी डिक्रीज हो जाती है। Characteristics of compressible fluids are density varies with pressure or temperature, volume change, high speed flow, shock wave, etc. और एग्जांपल इसकी एयर स्ट्रीम, नेचुरल गैस, रेफ्रिजरेंट्स, एग्जॉस्ट गैसेस। इनकम्प्रेसिबल फ्लूइड्स, इनकम्प्रेसिबल फ्लूइड्स को हम इनकम्प्रेसिबल इसलिए कहते हैं क्योंकि उनके मॉलिक्यूल्स एक दूसरे के काफ़ी नज़दीक होते हैं। जब भी हम उन पर प्रेशर या टेम्परेचर अप्लाई करते हैं तो उनकी जो डेंसिटी है उनमें सिग्निफिकेंट चेंज नहीं आता, इसलिए हम इन्हें इनकम्प्रेसिबल फ्लूइड्स कहते हैं। करेक्टरिस्टिक्स क्या हैं इनकम्प्रेसिबल फ्लूइड्स की? कांस्टेंट डेंसिटी, वॉल्यूम डज नॉट चेंज, सिंपलर इक्वेशंस, नो शॉक वेव्स। जबकि एग्जांपल्स ऑफ इनकम्प्रेसिबल फ्लूइड्स आर वाटर, ऑयल, मिल्क, ब्लड, लिक्विड मेटल्स एक्सेट्रा। इसके बाद आता है मैक नंबर एंड कंप्रेसिबिलिटी क्राइटेरियन। मैक नंबर क्या होता है? मैक नंबर इज द रेशियो ऑफ स्पीड ऑफ मटेरियल to the speed of sound. Basically, it tells us whether the fluid is compressible or incompressible. If the value of Mach number is greater than 0.3, then the fluid will be compressible. If the value is less than 0.3, then the fluid will be incompressible. इसके बाद आ जाती हैं इंजीनियरिंग एप्लीकेशंस of compressible fluids and incompressible fluids. Jet engines and aircraft systems work on the basis of compressible fluids. Compressible fluids हम जो यूज़ करते हैं जेट इंजन एंड एयरक्राफ्ट सिस्टम्स में, रॉकेट्स एंड मिसाइल्स में भी कंप्रेसिबल फ्लूइड्स यूज़ होता है, और गैस टर्बाइंस में भी कंप्रेसिबल फ्लूइड्स। वेल ऑन द अदर हैंड हाइड्रोलिक सिस्टम्स जिसमें हम ऑयल यूज़ करते हैं वो इनकम्प्रेसिबल फ्लूइड की एप्लीकेशन है। वाटर सप्लाई एंड मैनेजमेंट सिस्टम में भी हम ये अज्यूम करते हैं कि जो फ्लूइड है वो इनकम्प्रेसिबल है, क्योंकि हमें फ्लो रेट और प्रेशर डिफरेंसेस एनालाइज करने होते हैं, इसलिए जो फ्लूइड होता है उसे हम इनकम्प्रेसिबल ही अज्यूम करते हैं।
Okay, so now let's talk about the duct flow or the flow of compressible fluids in a pipe. तो इस फिनोमिना को गवर्न करने के लिए हमारे पास दो फ्लो कंडीशंस होती हैं। वन इज द एडियाबैटिक फ्लो एंड अदर इज द आइसोथर्मल फ्लो। एडियाबैटिक फ्लो में हमारे पास होता ये है कि वी डू नॉट ट्रांसफर एनी हीट विद द सराउंडिंग्स, लेकिन पाइप के इंटरनली हम फ्रिक्शन को इंट्रोड्यूस करा देते हैं। अब जो फ्लूइड के अंदर प्रेशर ड्रॉप और वेलोसिटी इंक्रीज आएगी, दैट इज सोली ड्यू टू द फ्रिक्शन इंट्रोड्यूस्ड रादर देन एनी टेम्परेचर चेंज। अगर इसकी मेजर एप्लीकेशंस को हम देखें, सो इट इज सीन इन स्टीम लाइंस एंड हाई प्रेशर गैस ट्रांसपोर्टेशन। नेक्स्ट वी हैव आइसोथर्मल फ्लो। आइसोथर्मल फ्लो में हम इंटरनल फ्रिक्शन को नेग्लिजिबल कर देंगे और एक हीट सोर्स को ऐड कर देंगे। अब जो डेंसिटी चेंजेस आ रही हैं फ्लूइड के अंदर, दैट इज नॉट ड्यू टू द इंटरनल फ्रिक्शन बट इट इज ड्यू टू द टेम्परेचर। लेकिन इस फ्लो में हमारे पास कंटिन्यूस हीट एक्सचेंज होनी चाहिए विद द सराउंडिंग्स। तो आगे हमारे पास है फेनो फ्लो एंड रियली फ्लो। फेनो फ्लो में वी हैव अ कांस्टेंट एरिया इन विच वी ऑब्जर्व एन एडियाबैटिक फ्लो। जैसा कि मैंने पहले बताया था कि एडियाबैटिक फ्लो में वी डू नॉट allow the heat transfer between the fluid and the surroundings, but we introduce the internal friction. अब that friction causes the pressure drop and the Mach number increases towards 1. Mach number is simply the ratio of speed of fluid to the speed of sound. Mach number increase करने का मतलब है कि we are approaching the speed of sound. अब जब तक हमारा flow speed of sound से नीचे नीचे रहेगा, the friction actually accelerates the fluid. एक टाइम आएगा कि एक्सेलरेट होते होते हमारा मैक नंबर 1 हो जाएगा, यानी कि द फ्लो इज नाउ सुपरसोनिक। एट दिस पॉइंट वी कैन नॉट फर्दर इंक्रीज द फ्लो ऑफ फ्लूइड एंड दिस पॉइंट इज कॉल्ड द फेनो चोकिंग पॉइंट। अब वंस चोक द मास फ्लो रेट कैन नॉट बी इंक्रीज। नेक्स्ट वी हैव द रेली फ्लो। रेली फ्लो में भी हम कांस्टेंट एरिया को ही कंसिडर करेंगे, लेकिन इन दिस प्रोसेस वी नेग्लेक्ट द इंटरनल फ्रिक्शन ऑफ द पाइप, but we introduce a heat source. अब the heat source will increase the temperature and specific volume of the fluid. Specific volume increase होने की वजह से हमारे पास fluid की density गिर जाएगी। डेंसिटी गिरने की वजह से अब mass flow rate तो हमें constant रखना है, तो the velocity will further increase. This can push the Mach number towards 1. अब Mach number इसमें भी 1 को अप्रोच कर जाएगा, यानी सुपरसोनिक फ्लो हो जाएगा. तो इस पॉइंट को भी हम रियली चोकिंग कहेंगे और इससे ज़्यादा हम फ्लो को इंक्रीज नहीं कर सकते. This is most relevant in combustion chambers, reheaters and flame tubes. अच्छा, तो मैं फाइनली अब ये कह सकता हूँ कि choked flow is a state at which the Mach number is equal to 1. यानी कि अब फ्लूइड की वेलोसिटी इज इक्वल टू द वेलोसिटी ऑफ साउंड, और ये दोनों फैनो फ्लो और रेली फ्लो में आकर हो सकते हैं. फर्दर लोअरिंग द डाउनस्ट्रीम प्रेशर विल नॉट इंक्रीज द मास फ्लो, यानी कि अब अगर आप चाहे टेम्परेचर बढ़ाएं या इंटरनल फ्रिक्शन ऑफ द पाइप बढ़ाएं, द मास फ्लो विल रिमेन कांस्टेंट आफ्टर दिस स्टेज. सेट्स मैक्सिमम फ्लो रेट थ्रू नोजल, स्टीम लाइंस, रिलीफ वाल्व्स, हाई प्रेशर गैस पाइपिंग. ये चारों वो एप्लीकेशंस हैं जिसमें प्रेशर ड्रॉप बहुत ज़्यादा होता है और हम मैक नंबर इज इक्वल टू 1 बहुत आसानी से अप्रोच कर सकते हैं. तो अगर इंजीनियरिंग एग्जांपल्स की मैं बात करूं तो गैस पाइपलाइंस में हम फ्रिक्शन ड्रिवन एक्सेलरेशन की वजह से चोकिंग ऑब्जर्व कर सकते हैं. स्टीम लाइंस में एडियाबैटिक बिहेवियर की वजह से चोकिंग ऑब्जर्व होगी. नोजल्स में चेंजिंग एरिया की वजह से सोनिक वेलोसिटी अप्रोच होती है, और कंबस्टन चैम्बर्स में रेली इफेक्ट्स की वजह से चोकिंग अप्रोच होती है, चोकिंग अचीव होती है क्योंकि हीट एडिशन होती है और हीट एडिशन विल इन्फ्लुएंस द मैक नंबर.
Assalamu alaikum sir, my name is Naim Abbas and I am going to present my topic nozzle flow. Flow through a variable area passage used to increase or control fluid velocity. As you can see in the picture that how nozzle flow converts pressure energy into kinetic energy. The main functions of a nozzle are very simple. It accelerates the flow sometimes to very high Mach number, and it helps produce thrust by increasing the exit velocity, and it also controls the mass flow rate. There are three basic types of nozzle: a convergent nozzle, which narrows and accelerates the subsonic flow, and a divergent nozzle, which widens and is used for supersonic expansion. And the third type, a convergent divergent nozzle, which first narrows and then expand, taking the flow from subsonic to sonic and then sonic to supersonic. Let's move on to the second slide. For nozzle analysis, we usually assume the flow is isentropic. This means that flow is adiabatic and reversible, so there is no heat transfer, no friction and no shock waves. This makes the equation simpler and gives us the relationship for pressure, density and temperature. The key relation come from the isentropic equation. Pressure and densities are linked through this equation. Density and temperature are linked through this equation, and density and temperature related by that equation. These equation helps us predict how the flow properties change inside the nozzle. You can also see in the picture we have a picture of converging diverging nozzle configuration, how the pressure, temperature and densities are linked together. Now we discuss velocity area relation and critical pressure ratio. So the velocity of flow in a nozzle is depend on the area of the nozzle and Mach number. When the flow is subsonic, Mach number is less than 1, reducing the area has the effect increasing the velocity. And when the Mach number is greater than unity, for supersonic there is an increase in velocity through an expanding area. And the throat, which is where the area is minimum, A is equal to A star, is the point where the flow reaches Mach is equal to 1. We have equation A over A star is equal to F into M. So we also have critical pressure ratio P star over P naught, which is equivalent to 0.528. Below this ratio, the flow at the throat is choked, meaning it reaches to Mach 1. Now moving towards the applications of nozzle flow. Nozzle flow appears everywhere in engineering. In rocket and jet engines, nozzle accelerate hot exhaust gases to create thrust. In turbines, nozzle increases the velocity of steam or gas before it hits the blades. And in the wind tunnels, especially shaped nozzles generate controlled subsonic or supersonic airflow for testing. And in many industrial systems, nozzles are used for spraying, cooling and mixing fluids or producing the fine droplets. Thank you so much.
Throttling. A throttling process happens when a fluid passes through a restriction This restriction can be a valve, a small capillary tube, a porous plug, or even a partially open orifice. When the fluid moves through this restriction, the pressure drops suddenly due to the decrease in the area. In throttling, there is no mechanical work produced, and usually we assume that no heat is transferred. Basically, we assume that it is an adiabatic process. Now, discuss the key characteristics of this थ्रॉटलिंग प्रोसेस. सबसे पहले जो मेन चीज़ होती है वो ये है कि ये एक आइसेंथैल्पिक प्रोसेस है जिसमें इनलेट के ऊपर और आउटलेट के ऊपर एंथैल्पी कांस्टेंट रहती है. And in this process, there is no heat transfer and no work done. And the changes in the velocity and height are usually very small, that we assume that the change in kinetic and potential energy are negligible. Because of these conditions, the fluid may either cool or warm up depending on its properties. This brings us to the Joule-Thomson effect. It basically tells us how the temperature changes when a gas expands through a throttling device. If the Joule-Thomson coefficient is positive, gas cools upon expansion, and if it is negative, the gas will warm up upon expansion. For example, the hydrogen and helium, they basically expand at room temperature. This effect is very important for cooling processes. Now we will discuss the importance of this throttling process. Throttling is useful because it reduces pressure without needing any external work. This makes it simple and reliable. It is widely used in refrigeration systems, chemical plants, and the oil and gas industry. और क्योंकि इसमें एंथैल्पी कांस्टेंट रहती है तो हम इसमें आउटलेट के ऊपर जो टेम्परेचर होता है उसको इजीली फाइंड आउट कर सकते हैं. Now we will discuss the industrial applications of this throttling process. In refrigeration, expansion valves create cooling for chillers and dehydration systems. और इसके अलावा जो अपस्ट्रीम और मिडस्ट्रीम ऑयल एंड गैस इंडस्ट्री में भी थ्रॉटलिंग का काफ़ी ज़्यादा यूज़ होता है, जैसे कि जेटी वेल्व्स में यूज़ होता है, जो कि गैस ट्रीटमेंट में काफ़ी ज़्यादा यूज़ होते हैं, स्पेसिफिकली गैस स्वीटनिंग में और नेचुरल गैस डिहाइड्रेशन में. और इसके अलावा फ्लैश सेपरेशन में भी ये काफ़ी ज़्यादा यूज़ होता है, जिसमें हम हाई प्रेशर फ्लूइड को एकदम से लेट डाउन करते हैं, उसका प्रेशर काफ़ी कम करते हैं, जिसकी वजह से फ्लैशिंग होती है और वेपराइज हो जाता है हमारा कुछ उसमें से लिक्विड. और इसके अलावा इन LNG एंड क्रायोजेनिक प्रोसेसिंग, दीज जेटी वेल्व्स आर पार्ट ऑफ द लिक्विफेक्शन, pre-cooling and NGL recovery because they provide auto refrigeration at very low temperatures. So overall, this throttling is a very simple but very important process which supports many major industrial operations.
Assalamu alaikum everyone. This is Sharjeel Gaur Khan, and in this section of the presentation, I am going to discuss how each of the thermodynamic concept that was discussed earlier by my group members is going to be implemented in a typical thermal power plant. The main purpose of a thermal power plant is to convert heat energy into mechanical energy, which is then converted into electricity. Now, depending on how this heat is produced, we have different types of thermal power plants. Although their energy sources are different, all of these plants operate on the same thermodynamic cycle, which is known as the Rankine cycle. The Rankine cycle has four essential components: the pump, boiler, turbine, and condenser. These components appear in every thermal power plant, regardless of the heat source. Now, most of the power plants use water as a working fluid because it is inexpensive, readily available, and has ideal thermodynamic properties. It also has a high value of Cp. From state 1 to 2, the feed water enters the pump. The pump's function is to increase the pressure of the liquid water. Since the water is incompressible, the pump requires very little work input, and the enthalpy rises only slightly. This matches with what Muhammad Amin and Muhibullah explained about incompressible flow and small enthalpy changes during pumping. So it is an isentropic compression process where the fluid pressure increases with minimal energy input. From 2 to 3, the high pressure water enters into the boiler. Here heat is added at constant pressure, which causes the water to heat up. The water undergoes phase change into steam and eventually becomes superheated steam. This is the major heat addition process of the cycle, and enthalpy increases significantly. The superheated steam produced here is sent
to the turbine. From 3 to 4, steam expands through the turbine. The steam flows through the converging and diverging nozzle-like turbine blades where the pressure drops, the temperature decreases, the velocity increases, and useful mechanical work is produced. And that work is later converted into electrical energy. This is a compressible flow process with large density changes, exactly as described in the topics on the nozzle flow and compressible gases. Ideally, the expansion is isentropic, meaning the entropy remains constant. So for state 4 to 1, the low pressure steam enters the condenser. Heat is rejected at constant pressure, causing the steam to condense back into the liquid water. Both the enthalpy and the entropy decrease during this process. The condensate is then sent back to the pump, which completes the cycle. Now moving towards the next slide, in which we are going to study the Rankine cycle with the help of the pressure enthalpy and temperature entropy diagrams. Let's go step by step. As we can see in the step 1 to 2, where the pump increases the pressure of the fluid, there is a slight increase in the enthalpy. This is not a significant increase, but there is a slight increase. On the other hand, with increase in temperature, we can see that the entropy remains constant. So it means that it is an isentropic process. For 2 to 3, we know that the high pressure fluid goes into the boiler where heat is added and phase change occurs, due to which the enthalpy is increasing, and with temperature increase we can see that the entropy is also increasing. The steam that is generated, it goes into the turbine where expansion occurs. So due to that, the pressure is going to decrease, and we can see that the enthalpy is also decreasing. On the other hand, we can see that the entropy change is constant. So we can say that it is also an isentropic process. So for 4 to 1, the fluid that goes into the condenser, it loses its heat. So because it is losing its heat and it is being converted from low pressure steam into liquid, so phase change is also occurring. So the enthalpy is going to decrease, and on this hand the entropy is also going to decrease. Now we have finally reached the slide in which we can discuss how each student's topic fits directly into a real Rankine cycle power plant. Starting with Muhammad Amin. His topic was thermodynamics of flow, particularly the steady flow energy equation and the enthalpy changes. This applies to every component of the power plant, the pump, the boiler, turbine, or the condenser, because all of them operate under steady flow conditions and rely on enthalpy differences for heat addition and work transfer. Mohibullah discussed compressible and incompressible fluids. In a power plant, steam flowing through the turbine behaves as a compressible fluid with large density changes, while water in the pump and the condenser is essentially incompressible. Abdurrahman's topic was a duct flow of gases. This appears in the long steam pipelines between the boiler and the turbine, where friction causes pressure drop and affects overall cycle performance. Qaim Abbas explained the nozzle flow, and this is directly relevant inside the turbine. The turbine plates act like a converging, diverging nozzle that accelerate the steam and convert enthalpy into velocity, and other useful mechanical work. Finally, Adam Abdullah covered the throttle flow. Throttling occurs in pressure-reducing valves used in feed water heaters and steam lines. It is an isenthalpic process used for flow control and conditioning. All of these concepts come together in the Rankine cycle, which forms the basis of a typical power plant.